October 29th, 2025, 11:47 p.m. UTC. Something impossible just happened in space. 3I Atlas. 24 hours ago, this interstellar visitor did something no comet should ever do. It turned blue, bluer than the sun itself. Scientists watching NASA's Stereo and SOHO spacecraft couldn't believe their screens. The data made no sense. Comets don't turn blue as they approach the sunday, they turn red, they turn orange. They get brighter, sure, but they follow predictable patterns. 3I Atlas shattered every single one. Click subscribe. What else is this object hiding? Drop your theory in the comments right now. In the next 45 minutes, you'll discover why 9 documented anomalies just became 10, why Harvard's most controversial astrophysicist is calling this unprecedented, and why December might answer the question that's kept humanity awake since July. Right now, at this very moment, 3I Atlas is behind the Sunday ground telescopes can't see it. Amateur astronomers can't track it. For the next 6 weeks, we're blind. But here's what we know from the last 24 hours. Here's what changed everything. Let's start with the brightening. Not normal brightening, explosive brightening. Between October 18th and October 29th, 3I Atlas increased in luminosity at a rate that breaks the rules. Scientists measure this using something called the heliocentric brightness index. For typical Oort cloud comets, that number sits around -4. Predictable, stable, expected. 3I Atlas clocked in at -7.5, ±1. Let that sink in. That's nearly twice the rate of change. This object is brightening so fast, so aggressively, that every model we have for cometary behavior just got thrown out. NASA's Goddard Space Flight Center confirmed this using data from multiple spacecraft. GOES-19, Stereo A, SOHO's LASCO coronagraph. All of them saw the same thing. All of them recorded the impossible. Here's the problem. Comets brighten because ice sublimates, water ice, carbon dioxide ice. As they get closer to the sun, heat converts solid ice directly to gas. That gas reflects sunlight. That's why comets get brighter. But the math doesn't work. Not for -7.5. That rate of change suggests something else is happening. Either 3I Atlas has a completely different composition than any comet we've studied, or the sublimation process itself is fundamentally different, or it's not sublimation at all. Dr. Thiem Huang from the Korea Astronomy and Space Science Institute has been tracking this object since July. According to emerging reports, his team spent the last 48 hours analyzing the brightening curve. They're looking at surface renewal, fresh ice exposure, materials buried beneath a thermal crust suddenly reaching sunlight. That would explain rapid brightening. But -7.5? That's extreme even for fresh ice. Now add the color shift. This is where it gets genuinely strange. On October 29th, exactly 24 hours before perihelion passage, multiple spacecraft captured 3I Atlas in visible wavelengths, SOHO's large-angle spectrometric coronagraph. The compact coronagraph, SECOR-1, on Stereo A. Both instruments recorded the same phenomenon. 3I Atlas appeared blue, not slightly blue, not blue tinted, strikingly blue, bluer than the sun's corona surrounding it. Comets don't do this, ever. Comets scatter sunlight through dust particles in their coma and tail. Dust scattering produces reddish or yellowish hues. The bigger the dust grains, the redder the color. That's basic scattering physics, Rayleigh scattering. The same reason Earth's sky is blue and sunsets are red. But 3I Atlas flipped the script. Blue emission dominated. Dust scattering didn't. The object glowed with a color signature that makes no sense for a natural comet at that distance. Here's what makes this suspicious. The blue shift happened exactly when 3I Atlas entered the field of view of spacecraft specifically designed to monitor the sun's corona. LASCO has been operational since 1995. SECOR-1 launched in 2018. Both instruments have observed thousands of sun-grazing comets. None turned blue like this. None showed this specific spectral signature. Dr. Avi Loeb from Harvard University has been vocal about 3I Atlas since its discovery. According to multiple sources tracking his public statements, Loeb noted that blue emission could indicate specific molecular processes, carbon compounds, cyanogen, diatomic carbon, C2, which emits strongly in blue wavelengths. But here's the problem with that explanation. C2 emission requires specific temperature conditions, specific solar radiation intensity. At one point, 3-6 astronomical units from the sun, at the moment of perihelion passage, those conditions are borderline. Most comets show strong C2 emission much closer to the Sunday, inside 1 AU, inside Earth's orbit, 3. I Atlas peaked at 1.36 AU. That's 203 million kilometers. That's between Earth and Mars. Something about this object's chemistry allows blue emission at greater distances than normal. Either its carbon compounds are more reactive, or there's another emission mechanism we haven't identified. The timing is remarkable. October 29th, exactly. Remember this date, 24 hours before the maximum thermal stress test. 24 hours before perihelion passage would subject 3I Atlas to 770 watts per square meter of solar radiation. Why did the color shift happen then? Why not earlier? Why not later? Scientists monitoring the object expected brightening as it approached perihelion. They expected increased activity. They did not expect a sudden spectral change from dust-dominated scattering to blue molecular emission. You might think this is just unusual chemistry. Exotic ice composition, carbon dioxide ice, sublimating differently than water ice. That's possible. That's the natural explanation everyone wants to believe. But here's what else happened in those same 24 hours. The diffuse halo expanded. SECOR-1 measurements from late September through October tracked a glowing envelope around 3I Atlas. Not the tail, not the narrow dust stream pointing away from the Sunday a spherical halo. Diffuse, extended, roughly 300,000 kilometers in diameter, 300,000 kilometers. That's 3/4 the distance from Earth to the Moon. Let that sink in. This interstellar object, with a nucleus estimated at less than 6 kilometers across, generated a glowing cloud of gas and dust spanning 300,000 kilometers. For comparison, Jupiter's diameter is 143,000 kilometers. 3I Atlas created a coma more than twice the width of the solar system's largest planet. The Spherix Infrared Observatory detected similar extended emission back in August. Between August 8th and August 12th, thermal imaging showed asymmetric outgassing, material jetting from specific regions of the nucleus, not uniform sublimation across the whole surface. Focused jets, active regions. That behavior continued through October. SECOR-1 confirmed it. GOES-19 confirmed it. The diffuse glow persisted, expanded, and intensified as 3I Atlas closed the final distance to perihelion. Here's where the water question comes in, because October brought another revelation, another piece of the puzzle that doesn't quite fit. Thank you for being with us. Please subscribe, share, and like. On October 7th, physicists at Auburn University published findings from NASA's Neil Gehrels Swift Observatory. SWIFT is an ultraviolet and X-ray space telescope. It's designed to detect gamma-ray bursts, supernovae, high-energy transient events. But in late September, SWIFT turned its ultraviolet instruments toward 3I Atlas. The team was looking for a specific signature: hydroxyl radicals, OH molecules. The byproduct of water sublimation under solar ultraviolet radiation. They found it. Clear detection. Unambiguous spectral lines. Water vapor was outgassing from 3I Atlas at a rate of approximately 40 kilograms per second, when the object was still 3.5 astronomical units from the Sunday. 40 kilograms per second. That's 88 pounds. Every second, continuous outflow, like a fire hose running at full blast. Except the hose is a 6-kilometer rock flying through space at 80,000 kilometers per hour. Professor Dennis Bodowitz from Auburn led the study. According to the published paper, this water detection marked the first time SWIFT's ultraviolet spectrograph confirmed H2O sublimation from an interstellar object. Oumuamua never showed water. Borisov did, but much closer to the Sunday. 3I Atlas started leaking water at 3.5 AU. That's beyond Mars. That's in the outer solar system where sunlight is weak and temperatures are frigid. Here's the problem. Earlier observations from August and September painted a different picture. Spectroscopic measurements from ground-based telescopes, particularly the James Clerk Maxwell Telescope in Hawaii, detected strong carbon dioxide emission. CO2 dominated the coma. Not water, not H2O. Between September 7th and September 14th, JCMT measured hydrogen cyanide production rates, HCN, a tracer molecule for carbon-rich ices. The production rate tripled in 1 week, from 1.5 times 10 to the 25th molecules per second, up to 4.5 times 10 to the 25th. That's a 3-fold increase in 7 days. The coma at that point measured 180,000 kilometers in diameter. Asymmetric, lopsided, jetting from active regions on the nucleus. So what's really outgassing? Carbon dioxide? Water? Both? How much of each? The ratios matter. They tell us where 3I Atlas formed, how cold its birth environment was, what kinds of ices dominated the outer disk of its home star system. If CO2 dominates, that suggests formation in extremely cold regions, beyond the snowline, beyond where water ice is stable, in the deep freeze of a protoplanetary disk's outer edge. If water dominates, that's warmer, more Earth-like, more similar to solar system comets. Right now, scientists are divided. The SWIFT data says water. The JCMT data says carbon compounds. Both data sets are solid. Both teams are credible. The observations don't contradict each other, but they don't align either. What would need to be true for both to be correct? 3I Atlas would need a layered structure. CO2-rich ice in the outer layers, sublimating first as the object entered the inner solar system. Water ice deeper inside, protected by an insulating crust, only reaching the surface and sublimating once solar heating penetrated far enough. That's possible. That's consistent with cometary science. But it requires a very specific thermal evolution, a precise sequence of heating, sublimation, and crust formation. or the composition varies across the nucleus. Different regions rich in different ices. Active areas jetting CO2, other areas jetting water. Depending on which region faces the sun at any given moment, different molecules dominate. That would explain the asymmetry JCMT observed. That would explain why Swift detected water while earlier observations emphasized carbon dioxide. But it raises another question. Why is this object so heterogeneous? Solar system comets show compositional variation, but not to this degree, not with such stark differences over short timescales. Unless 3I Atlas isn't a single coherent object. Unless it's a rubble pile, loose aggregation of smaller fragments, each with slightly different chemistry, weakly bound by gravity. That would make it fragile, structurally unstable, vulnerable to thermal stress. Exactly the kind of object that would disintegrate during perihelion passage, which brings us back to October 30th, today, 11:47 UTC. The moment 3I Atlas reached its closest point to the Sunday. At that precise instant, the object experienced maximum solar radiation, 770 watts per square meter. For comparison, Earth receives about 1,360 watts per square meter. 3I Atlas got roughly half that. Doesn't sound extreme until you remember this is an object rich in volatile ices. CO2 sublimes at 194 Kelvin. Water ice at 273 Kelvin. At one point, 36 AU from the sun, surface temperatures on the sunlit side of the nucleus would spike well above those thresholds. Explosive sublimation. Internal pressure building as buried ice turns to gas. Structural stress as thermal expansion fights against the object's weak self-gravity. If 3I Atlas is a rubble pile, it should fragment. It should break apart. Multiple pieces separating, each trailing its own tail, creating a spectacular display visible to spacecraft and, eventually, to ground observers. If it's a solid monolithic body, it might survive. Outgassing would be intense, but the nucleus would hold together. It would emerge from perihelion intact. We don't know which happened, not yet, because right now 3I Atlas is in solar conjunction. The sun sits directly between Earth and the object. Ground telescopes can't observe it. Too much glare, too much scattered light. The only eyes on 3I Atlas during perihelion passage were space-based coronagraphs. SOHO, Stereo A, GOES 1-9. The Parker Solar Probe's Whisper cameras. Punch, the polarimeter to unify the corona and heliosphere, which just launched this year. All of them were positioned to watch. All of them recorded data. But that data takes time to downlink, time to process, time to analyze. Right now, scientists are sifting through gigabytes of images, looking for signs of fragmentation, looking for brightness changes, looking for structural failure, or looking for survival. Because if 3I Atlas emerged intact, if it held together under 770 watts per square meter of thermal bombardment, that tells us something profound about its internal structure. It would mean this object is tougher than expected, more cohesive. Either the ices are mixed with refractory materials, dust and rock that provide structural support, or there's something about interstellar objects that makes them more resilient than solar system comets. Here's where the spacecraft observations become critical. Between October 18th and October 24th, SEACOR-1 on Stereo A maintained continuous line of sight to 3I Atlas as it approached perihelion. NASA's GOES 1-9 satellite, positioned in geostationary orbit 36,000 kilometers above Earth's equator, tracked the object with its solar ultraviolet imager. SOHO's LASCO C3 coronagraph picked up 3I Atlas on October 18th. The object appeared as a faint smudge against the star field, moving steadily sunward. Frame by frame, hour by hour, LASCO tracked its progress until the comet passed out of the C3 field of view on October 24th. For 6 days, multiple spacecraft maintained eyes on target. That's unprecedented for an interstellar object during perihelion passage. Oumuamua wasn't discovered until it was already outbound. Borisov was tracked, but not with this level of coordinated coverage. Why such intense monitoring? Because the scientific community learned from Oumuamua. When the first interstellar visitor passed through, we missed it. By the time astronomers confirmed its extrasolar origin, the object was already leaving. Telescopes scrambled to observe it, but the data was fragmentary, incomplete. We didn't make that mistake with 3I Atlas. From the moment of discovery on July 1st, observation campaigns were organized. Time allocated on major telescopes, space assets repurposed. The goal was total coverage, every wavelength, every phase of the object's passage, and it paid off. The last 24 hours prove it. The blue color shift, the rapid brightening, the extended halo, the water detection, all of these discoveries came from coordinated observations across multiple platforms. But here's what's genuinely unusual about the spacecraft monitoring. The timing of when 3I Atlas entered each instrument's field of view. CCOR-1 first detected the object on October 18th. That's 12 days before perihelion. For a comet at that distance, still 1.5 AU from the Sun, visibility in a coronagraph is rare. The object has to be bright, active, outgassing heavily. 3I Atlas was all of those things. But it was also exactly positioned. Its trajectory brought it into CCOR-1's field of view at the precise moment when continuous monitoring would capture the entire final approach to perihelion. Coincidence? Probably. Orbital mechanics is orbital mechanics. The object's trajectory was set billions of years ago when it was ejected from its home system. It had no way of knowing where human spacecraft would be in October 2025. But the timing is remarkable. If 3I Atlas had arrived 6 months earlier or later, Stereo A would have been in a different position. GOES-19 only reached operational status in 2024. Punch launched this year. The constellation of spacecraft that captured these last 24 hours barely existed 2 years ago. We got lucky, or we were ready. Either way, the data exists. The observations are real. The blue shift, the brightening, the water detection, all of it documented by instruments we trust. Now comes the hard part, interpretation. What does it all mean? Where do these puzzle pieces fit? 9 anomalies were documented before October 29th. Irregular rotation, non-gravitational acceleration, unexpected gas emissions, metallic traces, anti-sunward tail, brightness fluctuations, compositional contradictions, spectroscopic oddities, structural mysteries. On October 29th, we added number 9, the blue emission. Striking, unprecedented, defying conventional cometary behavior. Some researchers are calling for a 10th anomaly, the rapid brightening rate. -7.5 versus -4. That's not just unusual, that's off the charts. It might deserve its own category. So where does that leave us? 10 anomalies. An object that doesn't behave like solar system comets. Composition that shifts depending on when and how you measure it. Structure that might be fragile or might be robust. We won't know until December. That's when 3I Atlas emerges from solar conjunction. That's when ground-based telescopes can see it again. Northern Hemisphere observers. Dark skies, large apertures. 8 inches minimum, probably bigger. The object will be faint, magnitude 12 to 14, depending on how perihelion affected it. If it fragmented, it might be brighter, more surface area, more sublimation, multiple components, each contributing light. If it survived intact, it could be dimmer. Surface refreshed by perihelion passage, but no catastrophic outgassing. Business as usual for a resilient interstellar traveler. Either way, December gives us answers, or at least more data, more spectra, more astrometry, precise position measurements to calculate non-gravitational acceleration. Is the object still jetting? Is it maneuvering? Are the forces purely thermal, sublimation-driven, or is there something else? That's the question Avi Loeb keeps asking. Is this natural or artificial? He's been consistent since July. Test the object. Look for signs of technology, structural integrity, maneuvering, anomalous acceleration that can't be explained by outgassing. The blue emission adds fuel to that debate. Natural processes can produce blue light, cyanogen, diatomic carbon. Molecular emissions are well understood, but the intensity matters. The timing matters. The fact that it happened exactly 24 hours before perihelion, exactly when spacecraft were watching, that's the kind of timing that raises eyebrows. Not proof, not evidence, just timing. Coincidence. The universe is full of coincidences. Our brains are wired to see patterns even when none exist. But 9 anomalies don't feel like coincidence. 10 anomalies start to feel like something else. Each one individually explainable. Each one within the realm of natural cometary behavior if you stretch the definitions far enough. But together? All 10 happening in one object? That's where scientists start to disagree. That's where the debates get heated. By March 2026, when 3I Atlas passes Jupiter's orbit outbound, we'll have months of post-perihelion data, trajectory refinement, composition analysis, structural assessment. The picture will be clearer. Until then, we wait, we watch, we analyze the data we have. The spacecraft observations from October 18th through 29th are gold. Every frame, every spectrum, every brightness measurement. Teams around the world are processing that data right now. Tomorrow might bring new revelations. A press release from NASA, a preprint on RCIV, a statement from one of the observation teams. The blue emission is all over social media. Astronomers are talking. The public is paying attention. This isn't Oumuamua. That object came and went before most people knew it existed. 3I Atlas is different. It's bright, it's active, it's observable, and it's currently doing something no comet should do, turning blue behind the sun, while 9 other anomalies wait for explanation. That's where we are. That's what changed in the last 24 hours. But let's go deeper into what the spacecraft actually saw, because the details matter. The sequence of events matters. Understanding exactly how 3I Atlas behaved in those final hours before perihelion reveals something fundamental about this object. GOES 19 captured the first clear images on October 26th. The solar ultraviolet imager on board this geostationary weather satellite isn't designed for deep space observation. It monitors the sun's corona, solar flares, coronal mass ejections, space weather that affects Earth. But 3I Atlas drifted into frame, a moving target against the fixed backdrop of the sun's outer atmosphere. GOES 19's instrument team noticed it immediately. They adjusted imaging cadence, higher temporal resolution, more frequent snapshots. What they recorded was a comet accelerating its activity, not just getting brighter, changing, evolving. The coma expanded visibly from frame to frame. New jets appeared. The asymmetry JCMT detected in September became obvious in GOES 19 ultraviolet images, one hemisphere more active than the other, material streaming from specific locations on the nucleus, rotation bringing fresh ice into sunlight, triggering new outbursts, classic cometary behavior. Except for the intensity. Dr. Carrie Leese from Johns Hopkins Applied Physics Laboratory has studied comets for 3 decades. According to sources familiar with his recent comments, Leese noted that 3I Atlas displayed outgassing patterns reminiscent of dynamically new comets, objects making their first passage close to the sunday, virgin ice sublimating for the first time. But 3I Atlas isn't a solar system comet. It didn't originate in our Oort cloud. It came from interstellar space. So dynamically new doesn't apply the same way. The object has never been near our sun before, true. But was it ever near its home star? Did it orbit close to another sun billions of years ago before being ejected? We don't know its history. We only see its present behavior. And that behavior suggests ice that hasn't been processed by repeated solar heating. Fresh volatiles. Pristine material preserved in the deep freeze of interstellar space for potentially millions of years. That preservation is key. Solar system comets that orbit the sun repeatedly develop an insulating crust. Dust and refractory materials left behind as ice sublimates. Over multiple orbits, this crust thickens. It regulates outgassing. It controls how quickly heat penetrates to subsurface ice. 3I Atlas has no such crust, or if it does, the crust is thin, newly formed. The object entered the inner solar system for the first time this year. July 1st discovery, detected at 4.6 AU, already active, already outgassing CO2. That means sublimation started beyond Jupiter's orbit, beyond 5 AU, where solar heating is minimal, where temperatures barely rise above 100 Kelvin. CO2 can sublimate at those temperatures if it's exposed. If there's no protective crust, if the ice is pure and accessible, water ice requires more heat. That's why the swift detection at 3.5 AU was surprising. Water typically doesn't sublimate until comets reach 3 AU or closer. Mars orbit, inner solar system. But 3I Atlas broke that rule. 40 kilograms per second at 3.5 AU. Either the water ice was mixed with CO2, being dragged off by carbon dioxide sublimation, or the object was warm enough to sublimate water independently. Here's where the thermal modeling gets complicated. Scientists calculate surface temperature based on solar distance, albedo, thermal inertia. For a typical comet at 3.5 AU, surface temperature on the sunlit side reaches about 170 to 180 Kelvin. Water ice sublimates at 273 Kelvin under Earth atmospheric pressure. In vacuum, sublimation occurs at lower temperatures, but still requires around 200 Kelvin for appreciable rates. 170 Kelvin isn't enough, unless there's subsurface heating, radiogenic decay, aluminum-2,6, potassium-4,0, long-lived isotopes generating internal heat. But those sources are weak. They can't raise subsurface temperatures by 30 Kelvin. Or the albedo is wrong. Maybe 3I Atlas is darker than assumed. Lower albedo means more absorbed sunlight, higher surface temperatures. If the object's reflectivity is only 3 or 4% instead of the typical 6% for comets, that could explain water sublimation at 3.5 AU. Dark surfaces also explain the blue emission paradox. If the nucleus is very dark, nearly black, it absorbs most incident sunlight, very little reflection. The light we see comes from the coma, from gas and dust. Molecular emissions dominate over scattered sunlight. Blue C2 emission, blue cyanogen, blue diatomic carbon glowing against the darkness of space. That's what LASCO and CCOR-1 recorded on October 29th, not reflected sunlight, not dust scattering, pure molecular fluorescence. That interpretation makes sense. It fits the observations. It explains why 3I Atlas appeared bluer than the sun's corona. Molecular emission versus thermal radiation. Two different physical processes producing two different spectra, but it requires the object to be darker than most comets. And if it's that dark, why? What makes interstellar objects absorb more light than solar system comets? Composition? Structure? Surface texture? One possibility is organic material, complex carbon compounds, tolins, radiation-processed ices that turn dark reddish-brown over millions of years of exposure to cosmic rays. Interstellar space is bathed in high-energy particles, galactic cosmic rays. Particles accelerated by supernovae and active galactic nuclei. Over geologic time, these particles strike ice surfaces. They break chemical bonds. They create radicals. Radicals recombine into larger molecules. Organic chemistry driven by radiation. The result is a layer of dark, complex, organic material coating pristine ice underneath. When 3I Atlas entered the solar system, that dark coating absorbed sunlight efficiently. Surface temperatures rose. Sublimation accelerated. The coating cracked and flaked away, exposing fresh ice. Jets formed. Activity increased. That's a natural explanation. It's consistent with what we know about radiation chemistry. It's been proposed for Oumuamua. It could apply to 3I Atlas. But here's the problem. If this dark organic layer is common on interstellar objects, we should see it on all of them. Oumuamua should have been dark. It wasn't. Spectroscopic observations suggested a reddish color, similar to asteroids in our outer solar system. Not black, not carbon-rich. Borisov looked like a typical comet, dusty, reflective enough to see from Earth-based telescopes when it was still beyond Jupiter's orbit. No indication of an ultra-dark surface. 3I Atlas is different. If the dark surface hypothesis is correct, it's uniquely dark among the three known interstellar objects. Why? What's special about its history? Where did it come from? That it accumulated more organic material than Oumuamua or Borisov. Or maybe the darkness isn't about organics. Maybe it's metal, nickel, iron, trace metals detected in 3I Atlas's spectrum back in August. Keck Observatory observations, nickel emission lines. Stronger than expected for a typical comet. Metals don't make surfaces darker though. They make them reflective, shiny. Unless the metal is finely powdered, microscopic grains mixed with ice. That could reduce albedo. That could create a dark, metal-rich surface, unlike anything in the solar system. Why would an interstellar object contain more metal than solar system comets? Different formation environment, different protoplanetary disk chemistry. Maybe 3I Atlas formed around a metal-rich star. A second or third generation star enriched by previous supernovae. Our sun is metal poor compared to some stars. Only about 2% of the Sun's mass consists of elements heavier than helium. Stars in the galactic disk's inner regions can have twice that metallicity. If 3I Atlas came from such a system, its chemistry would reflect that enrichment. More metals in the disk means more metals in comets, more nickel, more iron, more refractory elements mixed with ice. When those comets are ejected and spend millions of years in interstellar space, cosmic ray bombardment could alter that metal. Oxidation, sulfidation, creating dark compounds. It's speculative. There's no direct evidence. But the nickel detection is real. Keck 2 confirmed it. Dr. Jordan Steckloff from the Planetary Science Institute commented on those observations. According to reports from late August, Steckloff's team analyzed the emission spectra carefully. The nickel lines were weak but present, consistent with cometary metal abundance, but on the high end. Then there's the anti-sunward tail. This might be the strangest feature of all. Discovered during Keck 2 observations in August, confirmed by multiple observation, runs through September. Comets have tails pointing away from the Sunday. That's basic physics. Solar wind and radiation pressure push gas and dust outward. The tail always points away from the Sun, regardless of the comet's direction of motion. Except 3I Atlas has a second tail, a faint structure pointing toward the Sunday. Not as bright as the main tail, narrower, but visible in long exposure images. An anti-sunward tail defying the rules. How is that possible? Radiation pressure pushes outward. Solar wind flows outward. What force could push material toward the Sun? Gravity? The Sun's gravity does pull on the comet, but it pulls on the nucleus, not on dust grains that have already been ejected. Once dust leaves the nucleus, it's subject to radiation pressure and solar wind. Both push outward. There's no mechanism to create an anti-sunward tail, unless the dust particles are charged. Electrically charged grains interact with the Sun's magnetic field. Magnetic forces can accelerate charged particles in unexpected directions, but that requires specific conditions. The dust must be small, micron-sized, highly charged. The magnetic field orientation must be just right. It's possible, but it's exotic. It's not something we see in normal comets. Or the tail isn't dust. Maybe it's gas, ionized molecules, plasma interacting with solar magnetic field lines. Those interactions can create structures that don't follow simple radiation pressure models. Plasma tails can show knots, disconnections, unusual geometries. But plasma tails still generally point away from the Sunday. Anti-sunward plasma structures are rare. They've been observed in a few comets during specific solar wind conditions, but not as a persistent feature. 3I Atlas showed this anti-sunward tail consistently through August and September. Multiple observation nights. Different telescope teams. Everyone saw it. Everyone confirmed it. The structure was real. What would need to be true for this to be natural? The comet would need to be producing charged dust or ions under unusual conditions. The solar magnetic field configuration would need to be just right. The comet's own magnetic environment, if it has one, would need to interact with the solar field. All of those factors lining up? Possible. Unlikely. But possible. Nature does improbable things all the time. We just have to understand the physics well enough to explain them. Or the feature isn't a tail. Maybe it's a jet. Material ejected from the nucleus toward the sun-facing hemisphere. A jet oriented toward the sun would look like a tail pointing sunward. Jets happen. Comets have jets. active regions on the nucleus blast material in specific directions, but jets are transient. They come and go as the nucleus rotates, as different regions face the sunday. A persistent sun-facing jet requires an active region that's always pointed toward the sunday. That means the comet's rotation axis is aligned with the sun direction. Highly specific geometry. Unlikely, but possible. So we have multiple anomalies that individually are explainable but collectively strain credibility. Blue emission, possible. Dark surface, possible. Nickel enrichment, possible. Anti-sunward tail, possible. Rapid brightening, possible. Water at 3.5 AU, possible. CO2 dominance, possible. Extended halo, possible. Irregular rotation, possible. 9 possibilities. Or 10, each one natural. Each one within known physics. But all 10 happening in one object? What are the odds? That's the question scientists keep asking. That's where the debate gets uncomfortable. Because individually, nothing about 3I Atlas violates physics. Collectively, it looks designed, engineered, optimized to be anomalous in every measurable way. That's not a scientific argument. That's pattern recognition. Human brains evolved to see agency, to detect intentionality. When we see multiple unusual features together, we assume causation, design, purpose. But the universe doesn't work that way. Random processes create complex patterns. Evolution creates apparent design without a designer. Galaxies look structured, but they're just gravity and gas. Life looks purposeful, but it's just chemistry and selection. 3. I-Atlas could be the same. Natural chemistry, natural physics, just unusual, just rare. An outlier object that happens to combine multiple low-probability features. Statistics says such objects should exist. In a galaxy with hundreds of billions of stars, with trillions of comets ejected over billions of years, eventually one will look like 3I Atlas. We just happened to be alive when that one passed through our solar system. Lucky, extraordinarily lucky, or unlucky, depending on your perspective. Because now we have to explain it. Now we have to figure out if it's natural or something else. Avi Loeb argues for the something else hypothesis, not because the physics is impossible, but because the combination is suspicious, because science progresses by testing hypotheses. You don't rule out possibilities just because they make you uncomfortable. If there's a 1% chance 3I Atlas is artificial, we should investigate. We should look for definitive signatures. Technology leaves evidence. Engineering leaves marks. Materials, structures, behaviors that can't be explained naturally. Structural integrity is one test. If the object survived perihelion intact, despite being rich in volatiles, that suggests internal strength, cohesion beyond what loose ice and dust can provide. Maybe it's natural. Maybe it's a monolithic chunk of solid ice. But maybe it's something else. Maneuvering is another test. If post-perihelion trajectory shows acceleration that can't be explained by outgassing, that's a problem. Natural comets jet. They push themselves. Non-gravitational forces are common, but those forces follow predictable patterns. Sublimation is strongest near perihelion. Jets point away from the sunday. The acceleration direction correlates with solar heating. If 3I Atlas accelerates in weird directions, at weird times, inconsistent with sublimation models, that's evidence, not proof. Evidence. Something to investigate further. Communication signals, electromagnetic emissions, radio, optical, anything artificial. SETI has been monitoring 3I Atlas since August. The Breakthrough Listen project allocated telescope time. They scanned multiple frequencies, looking for narrowband signals, looking for modulation, looking for anything non-natural. Nothing detected so far. Silence. But SETI observations are limited. Sensitivity thresholds. Frequency coverage. If 3I Atlas is transmitting at frequencies we're not monitoring, or at power levels below detection limits, we'd miss it. Absence of evidence isn't evidence of absence. The silence doesn't rule out technology. It just rules out loud. Obvious technology broadcasting at us. By December, we'll have new data. Ground telescopes will see 3I Atlas again. Spectroscopy will confirm composition. Photometry will measure brightness. Astrometry will track position. Over weeks and months, we'll build a detailed post-perihelion picture. That picture will either fit natural models or it won't. If it fits, the mystery deepens but remains natural. An unusual comet with unusual chemistry from an unusual birthplace. Rare, but real. If it doesn't fit, if the data contradicts natural explanations, we'll have to consider alternatives, seriously, without prejudice, following evidence wherever it leads. That's what science demands. Openness to being wrong. Willingness to update beliefs based on new data. Comfort with uncertainty. Right now, we're uncertain. We have observations. We have measurements. We have 10 anomalies and no unified explanation. We have competing hypotheses and incomplete data. We have spacecraft watching a blue comet behind the sun while scientists argue about what it means. That's where we stand on October 30th. That's the state of knowledge 24 hours after the blue shift, 48 hours after the brightening surge, 11 weeks after water detection, 4 months after discovery. Tomorrow brings new analysis. Next week brings new papers. December brings new observations. The story continues. The data accumulates. The picture sharpens. And somewhere behind the sun, invisible to us, 3I Atlas continues its journey, outbound now, moving away from perihelion, cooling, slowing its frantic sublimation, either intact or fragmented, either natural or something else. We'll know soon. December is coming. Telescopes are ready. Observers are waiting. The next chapter in this story is about to begin. What happens next depends entirely on what those December observations reveal, but we can outline the possibilities. We can map the decision tree. Each branch leads to different implications, different futures for our understanding of this object. Scenario 1. Fragmentation confirmed. Multiple components visible. Brightness surge from increased surface area. Spectral changes consistent with fresh ice exposure. Trajectory showing multiple debris streams, each following slightly different paths due to separation velocity. If this happens, 3I Atlas becomes a textbook case of cometary fragmentation. Not the first interstellar object to break apart, but the first one we watched do it. The data would be invaluable. Fragmentation mechanics. Structural properties of interstellar material. How these objects respond to thermal stress. The scientific papers would write themselves. Comparative analysis with Borisov, which remained intact. What's different? Composition? Structure? Size? 3I. Atlas is smaller. Estimated nucleus diameter under 6 kilometers. Borisov was larger, around 1 kilometer for the active nucleus, but potentially more massive overall. Smaller objects are more vulnerable to tidal forces and thermal stress, less self-gravity holding them together. If 3I Atlas is a rubble pile, weak gravitational binding, fragmentation makes perfect sense. Expected. Predicted by some models, Dr. Nalan Samarasinghe from the Planetary Science Institute has studied cometary fragmentation for years. Split nuclei, tidal disruption, thermal cracking. According to his published work on similar objects, fragmentation probability increases with volatile content. CO2-rich comets are more prone to breaking apart because carbon dioxide creates higher internal pressures than water ice. 3. I Atlas is 87% CO2 by mass in the coma. If the nucleus composition matches that ratio, internal pressure during perihelion passage would be extreme. Gas production rate hitting 405 kilograms per second. All that gas escaping from a 6-kilometer body. The pressure gradients alone could crack the nucleus. So fragmentation wouldn't be surprising. It would be the natural outcome for a volatile-rich, weakly bound interstellar visitor. We close the book on 3I Atlas. Natural comet. Interesting chemistry, important data, but fundamentally normal, except for the 9 other anomalies. Fragmentation explains structural failure. It doesn't explain the blue emission, the nickel detection, the anti-sunward tail, the rapid brightening before perihelion. Those features remain unexplained, unless they're all connected to composition. Exotic ice chemistry creating exotic emission spectra. High metal content from a metal-rich protoplanetary disk. Charged dust, creating unusual tail geometry. Everything traces back to where 3I Atlas formed. What kind of star system produced it? That's a satisfying narrative. Unified explanation. One root cause, multiple observable effects. Scientists like that. Occam's razor. The simplest explanation that fits all the data. But let's consider Scenario 2. Structural integrity confirmed. 3. I Atlas emerges intact. Single nucleus. No fragmentation. Brightness consistent with pre-perihelion models, or slightly elevated due to surface refreshing. Trajectory showing normal post-perihelion behavior. This outcome is more problematic. How does a CO2-rich, volatile-dominated object survive 770 watts per square meter without breaking apart? What holds it together? Internal structure must be stronger than expected. Either the nucleus is more coherent, bonded ice rather than rubble, or there's a refractory framework, rock, dust, something providing structural support. Both possibilities are natural. Both have precedent. Some solar system comets are surprisingly tough. They survive multiple perihelion passages. They withstand tidal stress during close solar approaches. Structural strength isn't impossible for natural bodies, but combined with the other anomalies, intact survival raises questions. Not proof of anything, just questions. Why is this particular interstellar object so robust? What makes it different from typical comets? Avi Loeb would point to this as supporting evidence for the technology hypothesis. A manufactured object would be designed to withstand thermal stress. It would have internal structure, reinforcement, materials chosen for durability. Natural objects don't choose their materials. They're whatever ice and dust happen to be in the protoplanetary disk when they formed. Sometimes that results in strong bodies, sometimes weak, luck of the draw. So intact survival doesn't prove technology. It's consistent with both natural and artificial origins. We'd need additional evidence. Trajectory analysis becomes crucial. Non-gravitational acceleration. Does the outgassing pattern match the observed acceleration? Can we model the jets, predict the forces, and have those predictions match the orbital data? If yes, natural explanation holds. Outgassing drives acceleration. Physics works. No need for alternative hypotheses. If the acceleration doesn't match sublimation models, we have a genuine problem. Either our models are wrong or something else is pushing the object. An internal propulsion system, controlled thrust, technology. That's a testable prediction. December through March observations will provide the data. High-precision astrometry. Position measurements accurate to milliarcseconds. Over 3 months, any anomalous acceleration will become apparent. Teams are already planning this. Observatories coordinating, time allocated, software ready to process astrometric data in near real time. The moment 3I Atlas emerges from solar conjunction, measurements begin. If anomalous acceleration is detected, the scrutiny intensifies. Every telescope we have points at this object. Radio telescopes listening, optical telescopes imaging, infrared observatories analyzing thermal emission, looking for anything unusual, any signature that can't be explained naturally. Scenario 3. No data. 3. I, Atlas, doesn't reappear. December observations find nothing. The object vanished. This would be catastrophic for science and deeply suspicious. Comets don't vanish. Even if they fragment, we see the debris. Even if they disintegrate completely, dust trails persist. Something remains. Total disappearance implies either complete vaporization, which is thermodynamically implausible for a 6-kilometer ice body at 1.36 AU, or the object changed trajectory unexpectedly, maneuvered, left the predicted orbit. Either option is problematic. Vaporization requires energy. Where does that energy come from? Solar heating at 770 watts per square meter isn't enough. Not for complete destruction of a kilometer-scale object. You'd need orders of magnitude more energy. Trajectory change without visible cause implies propulsion. Non-gravitational forces larger than what sublimation can produce. That's the technology hypothesis in its strongest form. The object actively maneuvered away from predicted orbit. This scenario is unlikely. Orbits are well determined. JPL Horizons calculates 3I Atlas trajectory with high confidence. Barring a major outgassing event or undetected close approach to a solar system body, the object will be where we expect it to be in December. But if it's not, every assumption gets questioned. Every calculation gets rechecked. And if the math holds, if the object genuinely deviated from predicted trajectory without natural explanation, we face an extraordinary situation. Extraordinary claims require extraordinary evidence. Carl Sagan's dictum. But sometimes, extraordinary things happen. The universe is under no obligation to match our expectations. If the evidence points to something unusual, we follow the evidence. So those are the 3 broad scenarios. Fragmentation, intact survival, disappearance. Each has implications. Each tests different hypotheses. Each moves our understanding forward, just in different directions. Now let's talk about what we're learning independent of 3I Atlas's fate. Because the data we already have is revolutionary. Regardless of what happens next, this object has taught us things we didn't know before July. Interstellar objects are chemically diverse. We knew this from comparing Oumuamua and Borisov, rocky versus icy. But 3I Atlas adds a new category, CO2 dominated. Volatile rich beyond anything in our solar system. The Oort cloud has CO2-rich comets, but not 87%. That's extreme. This tells us protoplanetary disks are more varied than solar system examples suggest. We have one data point for planetary formation, our own system. We build models based on that. We extrapolate to other stars. But those models are limited by what we've observed. 3. I-Atlas comes from a different system, different star, different disk chemistry, different volatile ratios. It expands the parameter space. It shows us that planet formation around other stars can produce bodies with compositions we don't see locally. That's important for exoplanet science. If protoplanetary disks vary this much in volatile composition, the planets they form will vary too. Atmospheres, oceans, the chemistry of potential life, everything downstream from disk composition changes. 3. I-Atlas is a probe, a sample of extrasolar material delivered to our doorstep. We didn't have to travel light years to get it. It came to us, and it's still here, still observable, still providing data. That's unprecedented. Water detection is another major result. Swift's ultraviolet observations confirmed H2O sublimation at 3.5 AU. Combined with earlier CO2 detections, we now know 3I-Atlas contains both volatiles. Layered structure. Compositional variation. This is direct evidence for complex thermal evolution in its home system. The object formed cold, captured CO2 ice. Then something happened. Maybe it migrated inward toward its parent star, warmed up enough to acquire water ice, then got ejected before further processing. That migration history is recorded in its ice composition, or the disk itself had radial compositional gradients. CO2 in the outer disk, water closer in. 3I-Atlas formed at the boundary, accreted both types of ice. Either way, the presence of both volatiles constrains formation scenarios. Dr. Dennis Bodewitz, who led the Swift observations, commented on this in the published paper. According to the text, the water detection was surprising given the object's CO2 richness. Most models predicted CO2-dominated objects would be water-poor, formed too far out, too cold for water ice condensation. But 3I-Atlas defied that prediction. It has water, significant amounts, 40 kilograms per second at 3.5 AU. Extrapolating to perihelion, water production probably exceeded 100 kilograms per second during closest approach. That's a lot of water for an object supposedly formed in the frozen outer reaches of an alien solar system. It changes our understanding of where water ice can exist in protoplanetary disks. It suggests water is more widespread than models indicate. And water is the key to life. Habitable planets need water. If water ice is common even in CO, two rich regions of protoplanetary disks, that improves the odds for life elsewhere. More planets with water, more opportunities for chemistry to become biology. So 3I-Atlas, regardless of its nature, is telling us the universe is wetter than we thought. That's a profound result. That's worth the effort of observing this object. That justifies the telescope time, the spacecraft observations, the scientific attention. The anti-sunward tale teaches us about dust dynamics, charged particles, magnetic interactions. Even if we don't fully understand the mechanism, the observation is real. It's been confirmed. It's published. Future theoretical work will explain it. Models will be developed. Eventually, we'll understand how comets can produce sun-facing structures. That understanding will apply to solar system comets too. We'll look back at archival data. We'll find examples we missed, subtle features dismissed as noise or artifacts. 3. I-Atlas makes us look harder. It makes us question assumptions. The nickel detection informs us about metal content in extrasolar comets. Keck 2 observations were definitive. Nickel emission lines in the spectrum. Weak but present. That means the nucleus contains nickel, either as metallic grains mixed with ice or as compounds. Sulfides, oxides. Nickel abundance correlates with stellar metallicity. Higher metal content in the parent star means higher metal content in the disk, in the planetesimals, in the comets. 3. I-Atlas likely came from a metal-rich star, somewhere in the galactic disk with higher metallicity than our Sunday. That narrows down possible origin systems. We can't pinpoint exactly where 3I-Atlas came from. The trajectory uncertainty is too large, but we can constrain the type of star system, metal-rich. Probably older than our Sunday second or third generation star enriched by supernovae. The diffuse halo, 300,000 kilometers across, tells us about mass loss rates, gas production, how aggressively this object is sublimating. The extended emission means high activity, sustained outgassing over weeks and months. That's unusual for objects at 2 to 4 AU from the Sunday. Most solar system comets show modest activity at those distances. Tails appear, but they're faint, small. 3. I-Atlas was blazing, visible in spacecraft coronagraphs designed for much brighter targets. That level of activity implies either high volatile content, which we know is true, or efficient heat transfer to subsurface ice. Efficient heat transfer requires good thermal conductivity. Most comets have poor conductivity. Fluffy ice and dust mixtures insulate the interior. Heat doesn't penetrate deeply. Sublimation is limited to the surface layers. If 3I-Atlas has better thermal conductivity, heat reaches deeper. More ice sublimates. Activity increases. What gives it better conductivity? Denser structure, less porosity, more solid ice, less fluffy dust. Again, that points to a coherent object, not a rubble pile. Solid ice body with minimal void space. That would explain both the extended halo and the potential for surviving perihelion intact. All these pieces fit together. Compositional data, structural inferences, thermal modeling, activity observations. They paint a picture of an object unlike anything in our solar system. Denser, more volatile rich, more active, potentially more robust. Natural? Almost certainly. The chemistry works. The physics works. Nothing requires artificial origin, but the combination of features is remarkable, noteworthy, worth studying intensely because it's rare, because we might not see another one like it for decades. Interstellar objects pass through the inner solar system roughly once per year. That's the current estimate based on Oumuamua, Borisov, and 3I-Atlas. 3 detections in 8 years. But most pass undetected. Too faint, wrong position, bad timing. We got lucky with 3I-Atlas. Discovery at 4.6 AU gave us months of advance warning. Time to organize observations. Time to allocate telescope resources. Time to coordinate spacecraft. That early detection was crucial. Atlas survey system deserves credit. Automated sky monitoring. Wide field cameras. Software designed to detect moving objects. Without Atlas, 3I-Atlas might have been discovered much later. Closer to perihelion, less time to observe. The name is fitting. Atlas discovered Atlas. The survey system found the object that bears its designation. 3I refers to Interstellar. The third confirmed. Atlas is the survey code, combined into 3I Atlas. Simple, memorable, appropriate for an object that's kept astronomers on their toes for 4 months. By the time this story concludes, we'll have a comprehensive dataset. Pre-discovery images from TESS, discovery images from ATLAS, ground-based spectroscopy from multiple observatories, Hubble observations, Swift ultraviolet data, JWST infrared spectra, JCMT radio observations, Keck optical and near-infrared measurements, ESA, Mars orbiters, watching from Mars, stereo spacecraft, SOHO, GOES 19, Punch, Parker solar probe, dozens of instruments, hundreds of scientists, thousands of images and spectra, all focused on one 6-kilometer chunk of ice and dust from another star system. The most intensely observed small body in history, more data per kilogram than any comet before it. That data will be analyzed for years, decades. PhD theses will be written. Careers will be built. New techniques developed. Models refined. Our understanding of comets, of protoplanetary disks, of stellar chemistry all advanced because 3I Atlas happened to pass through. And maybe, just maybe, we'll discover something truly extraordinary. Something that changes not just astronomy, but humanity's place in the universe. That's the outside possibility. The low probability scenario. The thing we can't quite rule out, because 9 anomalies are a lot. 10 is more. Each one explainable, each one natural. But together, they form a pattern. And patterns make us wonder. They make us ask questions. They make us look closer. December will bring answers, or it will bring more questions. Either way, we'll know more than we do now. We'll have data. We'll have observations. We'll have facts to replace speculation. Until then, we watch. We wait. We analyze what we have. We prepare for what's coming. We stay ready to be surprised. Because 3I Atlas has surprised us repeatedly. Every time we thought we understood it, new data arrived. New anomalies appeared. The blue shift on October 29th was the latest surprise. It won't be the last. This object has a habit of defying expectations, of breaking rules, of making us rethink what we know. That's what makes it fascinating. That's why thousands of professional and amateur astronomers are tracking it, why news outlets are covering it, why the public is paying attention. Because 3I Atlas represents the unknown, the unexpected, the reminder that the universe is stranger and more wonderful than we imagine. In 48 hours, new data will emerge. Preliminary analysis of perihelion passage. Did spacecraft capture fragmentation? Did SOHO see brightness spikes indicating structural failure? Did Stereo A record multiple components separating? Or did they see a single intact object, glowing blue, streaming gas and dust, surviving thermal hell that should have destroyed it? That image would be powerful, iconic. An interstellar visitor passing through fire, emerging unchanged, continuing its journey to the stars. Either image tells a story. Either result advances science. We win regardless of the outcome, because we learn, we discover, we expand human knowledge. That's the mission. That's why we build telescopes, why we launch spacecraft, why we spend billions on instruments that detect faint lights in the sky. Because those lights tell us where we came from, what we're made of, whether we're alone. 3I Atlas might not answer that last question. Probably won't. But it's part of the answer, part of the accumulating evidence, part of the long journey toward understanding our cosmic context. 3 interstellar objects in 8 years. 3 data points. Not enough for strong conclusions, but enough to start seeing patterns, to start asking better questions, to start designing better instruments, specifically to detect and study these visitors. The Vera Rubin Observatory comes online in 2025, full operations in 2026. Wide Field Survey Telescope, deep imaging. It'll detect interstellar objects earlier, farther out, giving us even more advanced warning, more time to observe, more opportunities to gather data. In 10 years, we might have dozens of interstellar detections. A population, statistics, distributions of composition, size, activity. We'll understand what's typical, what's rare, where these objects come from, how they're ejected, how many are out there. 3I Atlas is teaching us how to do this, how to coordinate observations, how to extract maximum information from limited observing windows, how to combine data across wavelengths and instruments. The lessons learned here apply to future objects. By 2035, interstellar object science will be routine, standard protocols, established procedures, networks of telescopes automatically tracking newly discovered visitors, maybe even spacecraft missions. Fast flyby probes launched to intercept objects while they're still in the inner solar system. That future starts now. With 3I Atlas, with the discoveries of the last 24 hours, with the blue shift that shouldn't have happened, with the 9th anomaly, with the questions that keep multiplying. Tomorrow, new data. Next week, new papers. December, new observations. March, comprehensive post-perihelion analysis. The story continues. The investigation proceeds. Science marches forward, one observation at a time, one measurement at a time, toward truth. And somewhere beyond the sun, racing outbound at 80,000 kilometers per hour, 3I Atlas continues its journey, unaware of the attention, unaffected by our theories. Simply existing, simply moving, simply being what it is. Whatever that is, we'll find out. We'll figure it out. We'll solve this mystery, because that's what humans do. We explore, we question, we discover. We don't stop until we understand. 3I Atlas turned blue. It brightened impossibly fast. It survived perihelion passage, or it didn't. Either way, it changed astronomy. It changed what we know about the universe. It reminded us that out there, in the vast darkness between stars, wonders exist. Mysteries wait, discoveries beckon, and we're ready. Telescopes pointed, instruments calibrated, scientists prepared. The next chapter begins in December. The next revelation waits just beyond the sun's glare. The next piece of the puzzle is coming. We'll be watching. We'll be ready. We'll catch it. We'll understand it. Because 3I Atlas isn't finished teaching us. Not yet. Not by a long way. The interstellar visitor that turned blue still has secrets, still has data to reveal, still has surprises waiting. December will show us. March will confirm. By this time next year, we'll look back at October 30th, 2025, as the day everything changed. The day the mystery deepened, the day we realized just how little we knew, and just how much there is left to discover. Thank you for being with us. Please subscribe, share, and like.